Well, hello, my Theosophical Society friends. It's nice to be with you again. So here I am, Jeff Curtis, coming to you again from the, excuse me, I'm a little bit hoarse today, from the Sierra foothills. And I'm going to spend a little while talking some more about this concept of cosmology and the Big Bang. I gave the title for this talk somewhat facetiously as in the beginning there was nothing which exploded, which is kind of a humorous take on the notion of the Big Bang, which I'm sure you've heard about in different contexts. And now it's a word in common parlance in the land, and people have sort of an idea what it means and what it comes from, and also the mystery that's involved in it. And it's a really deep and really interesting and sort of beautiful mystery. That's my cat Max walking around back there. Anybody wondered? He always likes to join in on these things. It's such a foreign concept. Big Bang. All of this universe, everything we see, us, the Earth, the stars, the planets, distant galaxies, it all came out of some initial point or singularity. That's really a strange thing to try to wrap your head around. And we're going to do this in stages. And what I'm going to continue here tonight is sort of ploddingly and slowly, and a little bit like a college lecture, since that's where I come from, explaining a little bit of why we know. To me, that's really important. We really want to have a sense of why we know what we think we know, because it's always subject to change. And never has it been more obvious that science is fluid, and we learn new things and we overturn old ideas and replace them with new ideas. It's a living, breathing entity, this body of knowledge that we refer to as science as a noun, but it's really a process. And so I'm going to spend a while tonight dovetailing off of what I spoke about last time in terms of the process of how we developed the science of cosmology and our notions of the very large. I find this a generally useful approach or educational paradigm to look at how we developed our sense of understanding and what we think of as a reliable body of knowledge with interrelated observations, and then thinking about those observations and building models in our head and bootstrapping ourselves along in a chain of understanding. The more times you study that in the course of a science education, or I would argue an observation and insight-based life, then the better of a sense you get of critical thinking and when to trust, or at least provisionally trust, an idea that at first seems ridiculous and maybe even brings about a certain amount of recoil, like a Big Bang. The word Big Bang was coined in derision by a fellow named Fred Hoyle, who back in the 50s was a major proponent of what was called the steady state universe. And he coined it in some talk that he gave as a way of kind of snidely pointing out just how ridiculous it was. And it stuck, and then observational data made it look more and more solid, and so here we are. It's with us, and it's part of standard language now, and yet the logical underpinnings are not very much appreciated or understood. Well, by the end of this evening, you're going to have a much better sense of where this idea comes from. So, as brief review, one of the main things I talked about last time was the idea of a redshift, and the fact that if objects are receding from each other at high velocity, if you emit a certain color of light from, say, this source, a receding receiver will register a longer wavelength light. And I went through the mathematics of that. So that's called the redshift. That idea figures prominently into what I'm about to explain tonight. The other idea that I got into last time was the notion of how we first measured distances between stars using parallax, which is the physical shifting of a nearby star versus very distant background stars. When we look at it from periods of time 6 months different in the Earth's orbit. So we're using essentially the diameter of the Earth's orbit as a baseline in order to view a nearby star 6 months apart in time and measure with a very, very accurate optical devices how much does that star's position shift relative to stars that are so far away behind it that we can call them at infinity effectively. And that developed for us the idea of stellar parallax and a unit of distance called the parsec. And you've heard that word used in science fiction shows. A parsec turns out to be the distance away something has to be in order to subtend 1 arc second of parallax. Turns out to be 3.3 light years in distance. And the light year is a quantity that most people are relatively familiar with. And it's the distance that light travels in a year. This parallax method was first applied to a star called Alpha Centauri, which happens to be almost the closest star to Earth. It has a very dim companion called Proxima Centauri that's even closer. But the brightest one that people could see back then in the 1800s was Alpha Centauri. Turns out to be 4.2-ish light years away. And that was achieved back in the 1800s. Well, then what? Okay, so as we wanted to try to look farther and learn more, came a set of observations and discoveries and highly collaborative work between lots of people. We could say that the next rung of our cosmic distance ladder in our ability to measure things knowingly rather than just guessing out into the galaxy sort of had its beginning in about 1784 with the discovery of certain kind of variable stars. So astronomers, they're very careful people and patient, and they observe things over long periods of time. It soon became evident once people started using telescopes in large numbers and looking out into the nearby realm of stars we have around us, that some of them seemed to vary in brightness. And so people dutifully measured the brightnesses, recorded that over time, and they developed what are called brightness curves. In other words, if you look at this star, it kind of goes between dim and bright with a certain period. A subclass of those emerged, of stars that all had about the same color and varied their brightness in a certain way, and they came to be known as the Cepheid variables. That's after the name of the constellation Cepheus, which is up there. It's one of the circumpolar constellations. It's near Cassiopeia, and this Cepheid star then was the progenitor of an entire class of Cepheid variables. And what happens with these stars is that they are of a certain size and temperature that there's sort of a chemical reaction takes place in the atmosphere around these stars, where helium in the atmosphere around these stars cycles between being doubly or singly ionized helium. So helium is the element with 2 protons. Therefore, the neutral form of helium has 2 electrons. But stellar atmospheres are very hot, and the gases present in the atmospheres of stars are very substantially ionized, so that the dominant form of the helium right in the atmosphere just above the surface of this star would go between helium-1 and helium-2, but when it absorbed enough energy to be helium-2, it became more opaque and therefore absorbed more light and trapped more heat, expanded, cooled, sunk back down, became helium-1, back in and out. So what's going on is that you have essentially a cyclic reaction being driven by photochemistry and temperature fluctuations. Well, those stars would pulse, and what people realized, particularly after the observational brilliance of a woman astronomer named Henrietta Swan Leavitt in the early 1900s, she used the best available telescopes at the time, and she was looking at the Magellanic Clouds. So if any of you have ever traveled to the southern hemisphere, you might, looking up at the stars, you would see a couple fuzzy patches. They'd look like little pieces of the Milky Way broken off and moved into the southern hemisphere. Called the Magellanic Clouds because Magellan was the first well-known person to report them, having been the first guy to sail that far south and observe them. Well, Henrietta Leavitt, she observed thousands of Cepheid variables in the Magellanic Clouds, and she had a team of astronomers. It was a group effort. Imagine how painstaking that is. They didn't have great electronic devices. A lot of this was done by just estimating brightness of stars between 2 other stars that were constant, and erecting in a very painstaking way these brightness scales. Well, she cataloged thousands of Cepheid variables in these little Magellanic Cloud things. The Magellanic Clouds are satellite galaxies. They're small, they're called dwarf galaxies. They orbit our galaxy. Eventually they'll be eaten by our galaxy, but they still exist in their own right for now. And they've been a source of a lot of good science over the years. Well, what came out after the astronomers, the astrophysicists who would model what was going on in stars, they came to realize that you could make a plot of the absolute magnitude, which is the magnitude of a star if it's 10 parsecs away. And so there's ways to correct. They used the distance ladder of parallax and deep observations of these Cepheids to erect this curve. So it says absolute magnitude varying on the y-axis, and then the days of pulsation rate is on the x-axis. What that meant was that by looking at nearby stars, they could come up with something very important. It's called a standard candle. If you measured the pulsation rate of a Cepheid star, you could know its magnitude, its absolute magnitude, in other words, being corrected for distance, the magnitude that it would be if it was at 10 parsecs, which is relatively close, right? So I'm making a very long story very short here, but this curve, the absolute magnitude versus pulsation rate, was used then as a way of reaching farther and farther out. And people were able to use this within the Milky Way in order to start mapping where the arms of the Milky Way are, because that's a major point of interest in terms of people trying to understand the structure and dynamics of the Milky Way. But then came a huge reveal, just a massively important step in our understanding of the universe was in 1923. Edwin Hubble who is the namesake of the Hubble Space Telescope, he used the 100-inch Hooker telescope. I'm waiting for my camera to focus on that. Well, it doesn't seem to want. There we go. The Hooker telescope, which is on Mount Wilson, and he was able to identify individual stars in what had been known as the Andromeda Nebula. So up until about this time, the argument was these patchy things we see in the sky when we point telescopes around, we'll find these little fuzzy patches. And I've already mentioned in here that a fellow named Charles Messier, a French astronomer, was the first to really catalog these fuzzy patches in detail. And there was a raging argument as to, well, some of them looked like they were gas clouds, puffs of gas that might be the progenitor of stars. Some of them were clusters of stars, which when you looked with a bigger and bigger telescope, you could see more and more that they were like little balls of stars. Those are called globular clusters. They're really beautiful to look at in a telescope. Some of them just were kind of weird looking, elliptical, or maybe a little bit of a hint of a spiral structure. They didn't seem to be gas, or nobody knew what they were. And it was about a third of the nebulae in Charles Messier's collection, and people didn't know what they were. The debate was, is all that stuff in our galaxy, in the Milky Way, this collection of stars we live in now? Or are some of those things other galaxies that are out even really far? Well, in 23, Edwin Hubble used the then best telescope on Earth, which was a 100-inch telescope on Mount Wilson, and not only did he resolve the Andromeda Nebula into individual stars, but then he was able to find and isolate, and he did this visually, Cepheid variables. A combination of visual observations, and also they did have photographic plates they could use to try to help them in their research back then. So people were already using telescopes to take pictures of the stars, but the photographic plates they were using were nowhere near as standardized or as sensitive as the kind of detectors we use now to do astronomy with. So this was just an extraordinary observational feat that Hubble did. He was a genius of a person intellectually in terms of his grasp of astronomy and cosmology, but he was also really well known to be an observational virtuoso, a genius in terms of the kinds of things he could do with a telescope. So, all right then, what's this mean? Well, you've got a Cepheid variable, it's pulsating at a certain rate. That means you could use this curve to tell you what its intrinsic brightness was. Well, you compare the intrinsic brightness, this so-called absolute magnitude, versus how bright it looks to you from where you are using the instrument you're using. That means you can compute the distance to that object, because you know absolutely how bright that star is. You know how bright it looks to you through your telescope. It's a simple one over the other, and you've well, actually corrected by a square law, and you know how far away the thing is. And so he was the first to come up with a distance estimate to now what was realized to be the Andromeda galaxy, not the Andromeda Nebula. This Andromeda galaxy is visible by naked eye, by the way. It's bigger in extent than the diameter of the full moon. So if you're ever out someplace really dark, like where I live, you look up, you see this thing, and it's visible in the summer months. And it's wheeling overhead. It's in the constellation Andromeda, which comes off one of the corners of the constellation Pegasus. towards the north. And so it's fairly easy to observe it, and especially easy to see with binoculars. So it's not an obscure object. And it's a member of what we call our local group. Now, that was a huge feat, but he was in no way finished, because then what he did was something that is just beyond brilliant. He realized all the things we talked about last time of redshifts, and the fact that we know that the atoms and molecules, well, this atoms in space, atoms and ions, have allowed quantum levels, and we know what those allowed quantum levels are about. We've spent years actually together discussing quantum mechanics and spectroscopy and transitions between allowed quantum levels. You can measure redshifts in things like other galaxies. What Hubble used especially were calcium emission lines, the calcium 2+ emission lines. It has two, one at 393, one at 396 nanometers. And you can identify those spectral lines in galaxies. This doesn't really apply, what I'm going to talk about right now is not being applied specifically to the Andromeda galaxy for reasons I'll get to. But galaxies a few times further out than that. What he did was he looked at galaxies out there a few times more distant than where the Andromeda galaxy is, and looked how much are the calcium emission lines shifted by, but also looking at Cepheid variables in those galaxies. And so what he was able to do was erect this plot, which is super important, classic plot in all of science, really. So what I've got there on the vertical axis, I'm calling it the recessional velocity. That comes from the redshift. So that recessional velocity is derived from the Z number, or the redshift value of those calcium emission lines. And it tells you how fast is that thing moving away from me, because it's a redshift. If it was moving toward you, you'd see a blue shift. But you don't have to look out very far. If you look at Andromeda itself, you actually get a slight blue shift, because our galaxy and Andromeda are closing, and we're headed towards a collision. We're gravitationally bound. One of these days, in a few million years, well, no, farther than that. I forgot the number. It's more than a few million. Maybe it's 2 or 3 billion years. The Milky Way and Andromeda are going to begin a process of merging. Some argue that they've already started to merge in their very outermost regions. But anyway, those are nearby gravitationally bound galaxies. You have to look out past. And what you find is that the galaxies out at a higher distance are receding from us, as judged by redshift. And then, using the Cepheid variables, you can calculate their distance and how far away they are. That allowed for this incredible plot to be arranged. And this is just a hand-drawn estimate of what his first plot looked like. So you can see there's a lot of noise in it. And then there's a line drawn through there using statistical methods. And you get a slope to that line, which is the recessional velocity divided by the distance away. And what jumps out there is that the farther away something is, as measured by Cepheid variable absolute magnitudes, the faster it's receding from us. Now, Hubble, he came up with a slope, h, the slope h0 is the Hubble constant. His came out to be 600 kilometers per second per megaparsec. Megaparsec is just a million parsecs. That's not the number we believe anymore. There were, it was observational heroism. The fact that he could do that at all is amazing. The fact that he was off a little bit in the actual numbers is to be forgiven, because what happened over time was our understanding of the Cepheid variables refined, the observational techniques for measuring their life curves got better, as did the ability to perfectly nail our absolute magnitudes. So it's changed a little bit. It's dropped from 600 to 70. Okay, what's the factor of that among friends? It's still pretty close. Factor of 9 or so. No judgment. It was some amazing work, and it was then, of course, extended, as you might expect. Now let's talk a little bit about um, how that might have been done. So the Cepheid variables were our first really well-established standard candle. There are a couple of other standard candles based on variable stars. The total matrix of methods used to erect the cosmic distance ladder is kind of dazzling. I don't have a good figure to show you that handy, but it's complicated flowchart of methods used at a given distance. One of the most important scientifically to come along was something called type 1a supernovae. And the type 1a supernova is a special kind of nova explosion where astrophysically we've figured out that it comes if you've got a white dwarf star circling another star, typically larger and more diffuse, but not always. There are multiple scenarios that give you type 1a behavior. But what the type 1a behavior is special about it is that it involves a white dwarf. Now, white dwarf is think of it as a stellar corpse. We know that the way stars work is that they have nuclear engines going where hydrogen is being fused into helium and it's creating heat and radiation, and that pressurizes the star and keeps the star from collapsing. A star is a big condensed gas cloud. It's got a lot of weight behind it, wants to collapse, and it does so until upon collapsing, it heats things up enough inside that the hydrogen begins fusing into helium. That creates an outward pressure, stops the collapse, and the star attains equilibrium and burns for however many millions or billions of years it's going to do. Turns out that the larger the gas cloud, the brighter and bluer and hotter the star that results, and the shorter it lives. There's a certain mass category of stars that is smaller than the mass of our sun, that burn their hydrogen to form helium, then the helium to form carbon. They go through a nova stage, and then where they puff up and get angry, but they don't blow apart. And they settle down into an object we call a white dwarf. So a white dwarf is a sub-sun mass star that ran through its life cycle, puffed up but didn't blow up, and then shrank down and cooled and became this object we call a white dwarf. So it's still hot enough to glow white. So it's hot, but it's extremely dense, and it's much smaller than it was before. The white dwarf stars, I don't have the figure on the top of my head, but they're not big. I think they're much smaller than the diameter of our sun. But they have a strong gravitational field. If that white dwarf was a member of a binary pair, so that it was orbiting a companion star, what happens is the white dwarf is orbiting this other star that still has a pliable plasma atmosphere, and the white dwarf is stripping off mass and stripping off mass. And so there's a continual mass flow from larger, not dead yet star, giving up mass onto this white dwarf. And that can go on for a certain period of time, depending on the exact circumstances. But eventually what happens is that enough mass gets accreted onto the white dwarf to hit something called the Chandrasekhar limit. And the white dwarf now explodes again. And it explodes because of runaway nuclear fusion that gets kicked off and now is powerful enough to blow the whole thing apart. And so this kind of nova, it's not as bright as some of the classes of supernova, but it's a bright event, and it lasts for periods of days to weeks and goes through a brightness curve, and it's identifiable. So astronomers looking around at stars and other galaxies will see these things popping off now and then and measure their brightness versus time decay curve. Well, using well worked out and accepted models of astrophysics, it turns out that these type 1a supernovae can also serve as standard candles. In other words, their absolute magnitudes at the peak of their light curve it is quantifiable. And by looking at and measuring their light curve, we can know within fairly reasonably good limits the absolute magnitude of that event. Compare the absolute magnitude of the event to how bright it was in our telescope. We apply the inverse square law, where brightness falls off as the square of distance, and you can run through a little algebra, and you can come up with a distance measurement. And this time, it works much farther out than the Cepheid variable thing can work. And that is what allowed for a huge extension of the cosmological distance ladder and the corrections to the Hubble plot that I showed you at first, and how does that slope go from 600, as observed over a relatively nearby set of galaxies using Cepheids, to a value closer to 70 when we use the best data we have over much longer distance scales now because of those supernova events. It's quite impressive, really, the team effort to this, the amount of brilliance, observational hours. I mean, a lot of major respect for the astronomical community and what they've been able to pull off and understand using these models and painstaking, massive, voluminous observational data. Okay, so now let's think about another implication of all this, and I'm bringing it in for a landing here, probably only another 8 or 10 minutes. How does this all make us think there might have been a Big Bang? Well, it's not too big of a leap, and I think I can sketch it out for you here now. Let's think back to some of the concepts that we've talked about at various other lectures in here together. One of them being definition of velocity. So a definition of velocity, you might recall, is just distance traveled over time. So v equals d over t, all right? How would we use that to come up in conjunction with this Hubble plot stuff to some kind of a concept of the age of the universe? Well, think now just a little bit fundamentally about the time since two things were touching. So if two things have been traveling apart at a constant rate, velocity, we just take the distance they're apart and we divide it by the velocity. So the distance apart, when we look at them, if we know the velocity that they've been traveling apart, boom, we know the time. So if you look at this algebraic expression here, I can take the t from below there on the right-hand side and swap it with velocity. And you see that t, time, is equal to distance divided by velocity. Well, okay, that's cool. Now, from that Hubble plot, we were just looking at the recessional velocity happens to be equal to the Hubble constant 0 times the distance. That was one of the points of this plot here. And so from that little bit of algebra, we can say, well, the time since a couple of galaxies were touching, t in this line, would be equal to the distance between those galaxies divided by the velocity, and wow, that's exactly the units of 1 over the Hubble constant. So if I just take the reciprocal of the Hubble constant, that's 1 over 70 kilometers per second per megaparsec. Now, I have to do a little bit of arithmetic. I won't bore you with. I'm going to have to convert from megaparsecs into kilometers. But what you get down to is that using this simple algebra, everything was touching 14 billion years ago. How about that? That's a remarkable, and yet quite clear, conceptual and algebraic pathway from Hubble's genius observation back in the day to the notion of how long has it been since everything was touching, based on the fact that we see everything flying apart. Okay? Now, a little bit about that. You can think of this flying apart business in two ways. One is, did something explode and send it all out? A bunch of matter into a pre-existing space-time structure of the universe? That intuitively, that's like thinking about a cantaloupe. If you put a firecracker in it and blow it apart, well, sure, some of it's going to be flying away faster, some of it's going to be flying away slower. You would see a spherical distribution of stuff all flying away with the outer regions having greater velocities. So that would sort of match what Hubble was seeing. We've since come to realize, this is bringing in Einstein's general relativity, that doesn't really work to explain what happened. In order to arrive at a most mathematically plausible explanation of what's going on, is we actually now, our best models are that we think about something happened, an initial singularity of we don't quite know what, wherein a whole lot of energy began erupting and creating space-time as it went. So we don't necessarily have to think about a pre-existing space-time continuum. It's more like this big bang event, or whatever it was, is creating space and time as its energy driving it is becoming more and more dilute while the volume expands. And so this leads to the idea of expanding space-time. And I said before that the Milky Way and Andromeda, there's no redshift between us because we're actually very slowly converging under the influence of mutual gravitational attraction. If you look another 2 or 3 or 4 times further out, however, you begin to see that the galaxies are receding. That's because what's going on is that space-time is being created between these objects. So they're still in a gravitational attraction, it's just that it's not strong enough to overcome the creation of space and time, which we think is happening, and thereby driving things farther apart. I'll revisit that. This is a subtle enough concept that it's going to take a little while to make sense of it and bring it in for a landing. There's also been refinements on the Hubble curve based on both theory and observation. And one of the things we figured out is that if we greatly expand the Hubble plot using all of the standard candles we now have at our disposal, and using the best theoretical models we have from general relativity, we think that early in the expansion of the universe, it moved slower because there was so much matter and energy concentrated in the relatively small volume of the universe in its early history. And then, at a certain point, and I forgot to look up about when that happened, but it's happening just about now, relatively recently in the history of the universe. Something else is kicking in, and the expansion is running faster. So I put a faint straight line there, and I'm showing you the corrections that modern cosmologists are pretty sure are there. This latter phase, where we've got an upward deviation in expansion rate, is being driven, we think, by something called dark energy. This is based on observations of supernovae farther and farther out. And what we begin to pick up on is that if we get really out there to the farthest distance we can measure these supernova light curves, it seems that the universal expansion rate is accelerating. It's not going at a constant rate of acceleration. There's a time rate of change to the outward expansion. Fascinating. That bears directly upon modern speculations about the fate of the universe. For a long time, there's been an argument about whether the universe would just keep on expanding or reach a certain extent and then reverse and come back together into a big crunch, which would be an interesting end to the Big Bang, right? There's a certain pleasing symmetry to that. There was speculations, would time start running backwards if the universe began to recondense back towards the Big Bang type of, at least size. Now it looks like that's not going to happen, based on, this is really only about 25, 30-year-old discovery, this dark energy. Dark energy is just used as a placeholder. We don't know what's actually causing the universe to accelerate outward. There are mathematical hints. Einstein had a suspicion that that might be the case in some of his early formulations of general relativity. He included something he called a cosmological constant, which works out to be the same thing as this dark energy. Some of the thinking now is that we can calculate that very probably there will be a big rip at some point. The universe will get bigger and bigger and start accelerating faster and faster, and everything will fly apart. Others argue, no, that won't happen. The gravitational attraction will still keep things like galaxies together. So we're not going to be seeing atoms ripped apart, but we will be eventually in a universe where you can only see things relatively nearby that are gravitationally bound enough to fight off the expanding space-time in between objects. That's there in the realm of argumentation and speculation still. But okay, I think I've got to the end of my time. I hope maybe now, next time you hear the word Big Bang, you're going to at least have a sense of why we believe in the Big Bang. Now, I haven't come anywhere close to talking about why is it that nothing exploded. I'm going to move into that in my next talk or two. That'll involve deep discussions of the nature of the vacuum. And what is a vacuum? What is nothing, in other words? What do we know about quantum mechanisms that might allow for nothing to explode and create a universe. And it's not like that's all worked out, but there are at least some plausible speculations and ideas floating around out there. And we'll get to those and talk about them next time. So I hope you folks all have a great evening, and I'll see you in 3 or 4 months, and we'll pick it up and move it along some more. Thanks. Bye-bye.